Today we're going to start talking about how to solve PVTn problems. So the P stands for pressure, the V stands for volume, T temperature, and N, that's that amount. So in order to start, what we first want to do is this a PVTn problem? Is this asking me about gas, pressure, temperature, volume, those kind of things? Because these are all for solving things that are related to changes in gas variables. Once I've identified that it is a PVTn problem, I'm going to read the problem fully and start to put it down on my PVTn chart. So I'm going to start to make this chart right here. I'm going to pull the information down. If it's something that I start with, it goes in the initial category. If it's something I end with, it goes in the final. And just a quick thing to remember, we should only ever see Kelvin on our charts. We should never see Celsius or Fahrenheit or anything like that. I'll typically, if it's a problem I'm giving you, I'll only give it to you in Celsius, and you'll have to convert to Kelvin. So degrees Kelvin plus 273, and that'll equal your Kelvin final. So please put those onto your chart. And remember, that's because Kelvin is the one that makes our gas laws all proportional to each other. So then the next thing we have to do is start looking at the relationships. So I've filled it out. There's one over here that has its initial filled out, its final filled out. What did it do? And what am I trying to figure out? What's the response to that? So is it a direct relationship? Is it indirect? So if I raise volume, pressure should go down. If I raise temperature, volume should go up. Those kind of things are the things you want to ask yourself. Then you want to place the number you want to change out front. So the one that you don't know the final for, you're going to put that initial number right over 1. So if I started with 12 psi and I want to know how much pressure at the end, I'm going to put 12 psi over 1 and then put my next bracket there. The one I do know, that's the one that I'm going to use to help me convert. So the one that I have an initial and a final filled out for, that's the one I'll use. And it just goes to the relationship here of what happens to it. So if I raise volume, pressure should go down. So in this case, the big number should go on the bottom. If I raise temperature, pressure should go up. So it should go up. So the larger number should go on the top here, because it has to be either bigger or smaller than its starting point. And you know, because you know the relationship, whether it should go up or down. When you're done, remember to calculate the numbers. So we got to multiply everything on the top, the numerator, and divide by everything on the bottom, the denominator. Put the equal sign there. Make sure you put it down through your calculator and put it out. And then take that unit and put that unit on the end as well, because all of these are just proportionally related to each other. And we want to use those proportions to figure out how much this is. So let's actually do a couple together. So step 1 was know that we have a PVTn problem. Obviously, I have a PVTn chart here. I'm going to have to use it to solve this problem. But you could tell because it's asking you about volume and pressure, and that's a good giveaway for me. So what are some things that I'm given? So what would the new pressure, so I already know that the new pressure, so I don't know this one. So what would the new pressure if 250 cubic centimeters, so 250 cubic centimeters, because I know that that is my starting volume of gas at standard pressure. What's that? And then is compressed to a volume of 150 centimeters cubed. So what's a standard pressure? So we got to look up at this chart. So standard pressure is any one of these pressure values. Standard temperature is right here, 0 degrees Celsius or 273 Kelvin. Okay, so we use the term STP to say that sometimes. So I'm going to pick 1 because that's like the easiest one to work with, 1.00 ATM. And it's not saying it needs to be in a specific type of pressure, so I can pick and choose which one I want to do. Okay, so what's happening here? So I'm going to look toward my final column here. So I have a final filled out. So I'm on step 3. I'm trying to figure out what the relationships are. The volume is going down, and we know if volume goes down, that's going to increase our amount of collisions, so pressure is going to go up. Okay, so step 4, we're placing the number you want to change out front. So I need to change this number because this is the one I don't know here. So I'm going to place that 1.00 ATMs over 1. The next one, I'm going to start to look at what I have. So I have that initial final here. And this could be written as either 250 over 150 or 150 over 250, depending on what's happening, right? And we know we need a bigger number, so you choose the one with the larger number on top. 250 over 150, and that's going to be what it equals. So I put this in my calculator. I put 1 times 250 divided by 1 divided by 150, and that gives me 1.67 ATMs. Remember that my units are attached there. Great, let's do another one together. So we have a sample gas, and it occupies 150 milliliters at 25 degrees Celsius. What is the volume when the temperature is increased to 50 degrees Celsius? Don't forget to convert to Kelvin, always. So let's put what we have in. I have 150 milliliters. That's the initial. I have 25 degrees Celsius. So 25 degrees plus 273, and that equals 298. So my starting temp is 298 Kelvin. And then my next one is 50 degrees plus 273 equals, and that's 323 Kelvin. These should be Kelvin. And that's my ending, so 323 degrees Kelvin. What happened? So let's start looking. All my numbers are pulled down into the chart. Notice I'm not filling anything in pressure. I'm not filling out anything in amount, so we can ignore those. My temperature went up, and when temperature increases, volume also increases the speed. It's going to push against the sides of the container if it's flexible, right? And then how can this be written? So it can be written as 298 over 323 or 323 over 298. We know it needs to go up, right? So let's put this out front over 1 first. We know this number needs to increase, so that we're going to pick the one with the bigger number on top first, 323 over 298 equals, so I plug all that in my calculator, 150 times 323 divided by 1 divided by 298, and I should get 163 milliliters. It might be a little different than that. That's okay. And that's how I'm doing these. So I'm really just taking a just step-by-step kind of approach to this. Let's do one more together, okay? So the pressure in a bicycle tire is 105 psi at 25 degrees Celsius. You take the bicycle up to Huntington, where the temperature is -5 degrees Celsius. What's the pressure in the tire now? So let's start looking. So the pressure started at 105. And it was at psi. Then it was at 25 degrees Celsius, so 25 plus 273 equals, we did that one before, so that's 298 Kelvin. And so we're going to put 298 Kelvin up there. It doesn't say anything about volume, doesn't say anything about amount, so we can scratch those out. I want to know what the pressure is, so I'm not given anything in that, right? And then lastly is, this -5 degrees. So -5 degrees Celsius plus 273, and that should equal 268 Kelvin, right? So the temperature went down. Temperature goes down, the speed of the particles slow down, so therefore we're going to have less collision, so pressure is going to go down. And so we got to figure out what this is. So we got to put that 105 psi out front over 1. This one right here can be written as 298 over 268 or 268 over 298. We know it needs to go down, so the bigger number should go on the bottom. So that's 298 over 268. So 105 times 268 divided by 298, because 1 is just going to be the same, 94.4 psi. And we can even check. This was supposed to go down. Did it go down? Yes, it is a lower psi. So, and by how much, right? So it went down a little bit, so this should go down a little bit too. So we can use those kind of relationships too. So we can kind of even eyeball some of these. But if we want an exact number, we obviously have to do the math. But we should be able to check our work just by knowing what the relationships are. What are the particles doing? So we need to think about that every step of the way. All right, so these are the examples. So if you have any questions, please don't forget to ask in class. But really what it comes down to is taking just a step-by-step approach. Put the things on your chart, read the problem, identify the relationships, put what you want to change out front over 1, use that relationship, should it go up or down, and then calculate what's going on. So the numerator gets multiplied by the denominator gets divided at the bottom. All right, we'll see you soon.